Hello, everyone. My name is Juho Nurminen, and this is app setAsDefaultRCE client. For the next 45 minutes or so, I'm going to be talking to you a little bit about Electron, scheme handlers, and how to exploit those in apps to gain remote code execution. This talk is based on research I started working on in early 2019, and this is the first time I'm able to talk about it publicly. But most of the vulnerabilities you'll be seeing here have already been fixed, some of them even before I ran into them. The interesting thing about that is, though, that Electron hasn't really published any advisories about them. So developers mostly aren't aware that there are any issues, and there's no incentive to fix those outdated apps, and so old versions of Electron are still being used. In the name of transparency, I should also mention that literally a week ago I joined one of the companies building one of the apps named in these slides. So there's sort of a conflict of potential conflict of interest there, but all the research was made before I joined the company, and that hasn't really affected anything I'll be presenting here today. Let's start off with a quick introduction to Electron and Neuron. Now, that may sound like nuclear physics or something, but really the only thing these two have in common with nuclear physics is the end result if you don't know what you're doing. I'll demonstrate that a bit later on, but basically no one likes a nuclear meltdown. So anyway, if you're not familiar with Electron, what it essentially is just a hybrid desktop app framework. It lets you write HTML and JavaScript and make desktop applications using those web technologies. Without going into too much detail, it's technically just the Chrome browser bundled with Node.js and some custom APIs. Then there's also Neuron, which is, well, it originally started as an Electron fork with better security, but it's just a fork of Electron. And the unfortunate thing about that is that even though the original intentions were good, they wanted to harden Electron. The Neuron fork is no longer now maintained, and that means it's hopelessly outdated and vulnerable to all kinds of things. So while Electron is certainly more popular of the two, Neuron still has its users also, and those users aren't getting any security patches. So a while ago, in 2018, Electron patched a CVE, conveniently named CVE 2018-1,000,006. And this was a remote code execution vulnerability that was affecting Windows. And at the root of it was an API call named app.setAsDefaultProtocolClient. Invoking that function, app.setAsDefaultProtocolClient, would register your application as the default scheme handler for a particular URI scheme. And you could use it, for example, to set your application as the default mail-to handler for your email, or you could use a custom scheme to support deep linking in your chat app. That actually seems like a fairly common use case, deep linking. But the way the API actually does its trick is by looking up a key in the Windows registry based on the scheme handler that's being registered, or the scheme itself. And then it sets a value to point to the executable that should be executed when one of those types of links is clicked. And in order to pass the actual URI to the executable, it uses a simple format string where here you have %1, which would just then end up being replaced with the URI itself. So that actually means that because it's a sort of a naive replacement, if you include any special characters like double quotes or spaces in that URI, you end up injecting additional command line parameters or switches. What that actually entails for your application depends on the command line switches your application supports. But in the case of CVE 2018-1,000,006, it turned out that Chrome, which is bundled with Electron, natively supported launching arbitrary commands from the command line. So you'd have a remote code execution vulnerability simply by clicking a link. In practice, the way it would work, you'd have a crafted URI like this one, which points to the vulnerable URI scheme. And it contains a double quote, a space, and the -- GPU launcher switch. All that needs to happen is for the user to click on this link on a machine that has the vulnerable application installed, and Electron just does the rest. That happens. So really simple. This was obviously patched already. Way back in 2018. But the way Electron decided to approach the patching was somewhat interesting. The original patch was actually nothing more than a blacklist of all known command line switches that Chromium supported natively. That was over 1,300 switches, and it's just a list of those switches in the source code. And that was obviously very easy to bypass. There were plenty of bypasses and have been already, and some have been found later. Let's look at some of those bypasses in just a moment. Just a second, my slides froze. Yeah, let's look at some of those in just a moment, but before I get to the actual meat of this presentation, I just want to credit some other folks who have done research in this area. So Doi and Sec were probably the first ones to actually bypass CVE 2018-1,000,006. And they have a public write-up of the bypass on their blog. They also published this tool called electronegativity that's available also online. It's open source. There was also a very interesting talk by Thomas Shadwell at Infiltrate 2019. He talked about modern desktop applications. So the scope of that talk was a bit wider than mine is here, but it's worth looking. It's available on Vimeo if you like to see it afterwards. And then there's a talk from Andreas Lind from Security Fest 2016, where he talked about hacking Mattermost, which is actually one of the applications I'll be talking about here as well. Anyway, back to the matter at hand. As it turns out, in February 2019, when I started looking at these apps, plenty of them were still vulnerable to something awfully similar to CVE 2018-1,000,006. And what I have for you is 3 separate cases, sort of examples. 2 of them are specific to certain applications, and 1 is more generic, affecting Electron as a whole. So let's start from the top. The first one is Mattermost. Mattermost is a chat app, sort of like Slack, but open source and self-hosted and whatever. And like Slack, it has a desktop client that's built on top of Electron. There were three things in that desktop client that led to RCE when combined. First of all, the Mattermost desktop app has a command line switch that allows you to specify a custom user data directory. This is where the application stores all its local data, including configuration files and anything that's stored locally. There was no bug here, but it's an important part of the exploit chain anyway. Secondly, because we're talking about Windows here, UNC paths are supported. Universal Naming Convention, or UNC, is just a different way of specifying file system paths. But there's a twist to that, which is that unlike local paths, UNC supports network paths, so SMB shares on remote servers. And Microsoft even often refers to UNC paths as network paths. Thirdly, the application was loading configuration files in an insecure way, so that if you're able to inject malicious stuff into your configuration files, then you could gain code execution. This was actually a bug, and this has been fixed. And Mattermost has also implemented some additional mitigations, but I won't go into those in too much detail. So these are screenshots from the source code of the Mattermost desktop client. These are from the same source file from a piece of code that loads a configuration file and tries to restore the options of a previously closed window. So at the top, you can see how it's accessing the file system and loading a bounce.info.json file, and then parsing that using the JavaScript native JSON parser. At the bottom, you can see how it's then passing that object directly to the browser window constructor. There's no validation in between. It's just being read from the file and then being passed to the constructor. The idea here is to set the dimensions of a window that's been previously closed so that you can always have the same size windows. But if you look at the Electron documentation, this is from the browser window API documentation. There's something that's rather concerning, namely that the options parameter here, which was just read from a file and then being passed into the constructor without any validation, it supports plenty of other options besides just window width and height. So, for example, there's web preferences. And web preferences is an object that contains another property, which is called preload. And the preload property, well, the documentation for that says that any script that the preload property refers to is loaded automatically and executed, which is sort of really bad. But then it also has automatically access to all Node.js APIs, regardless of your sandboxing settings or anything else. So these preload scripts always have access to the privileged APIs. And Node.js means native code execution as well. So to put it all together, we start again with the crafted URI. The URI contains a double quote, a space, and then the injected command line switch, which is --data dir. But then the value of the switch refers to a UNC path on a remote server on an attacker-controlled SMB share. So when a user clicks on this link, the application starts up and starts loading configuration files and writing configuration files. But those aren't local, those are actually on the network, on someone else's SMB share. And the bounce info JSON file is loaded. The bounce info file refers to a preload script named payload.js, and that's automatically executed, which means, you just got owned. The next app, example number 2, I unfortunately can't name this one. They didn't fix their vulnerabilities in time, mainly because they're still using Muon, which is an unmaintained fork, and it's a pain to migrate away from that. So, yeah, I can't name the application, but I'll still talk about the interesting technical details here. So, the attack starts with a fairly similar pattern. The executable supports a command line switch to specify the user data directory, just like the previous app. And it accepts UNC paths, so you can specify a network path. But what's different here is that there wasn't anything in the configuration files that could be used to trigger code execution directly. So I had to come up with something else. What turned out interesting was that the developers had made some assumptions related to how Windows processes local paths. So Windows is fairly restrictive when it comes to file system paths. You can't have too many special characters in directory names, for example. But when you have UNC paths, you can have files that are somewhere remote, and the remote server doesn't have to be a Windows. So what if you have a Linux server that's naming files in a Linux way, and then you have a Windows client that's loading those files and assuming that your files can't have any funny names? That's where things go wrong. So, yeah, suddenly the developer's assumptions no longer held. Here's, again, a screenshot of the source code. This is from the debugger. I've had to alter it a little bit so that I wouldn't reveal the name of the application. But it's pretty easy to spot where the actual injection here happens. The code is calling PowerShell directly and then passing the user data directory into a PowerShell command as is without any validation. But the interesting part is that before this code was executed, there were file system operations happening locally that were using this path. So if that path wasn't a valid path, then the application would crash earlier on. And that meant that you couldn't inject, for example, double quotes or the dollar symbol, because those aren't valid as local path names. But they are valid as UNC path names, because UNC paths can refer to Linux servers. So let's exploit this one. Again, we have a crafted URI, and we inject the user data path. But now also the user data path contains an injection. It's referring to a remote server, and it contains a dollar symbol and a parentheses and a calc.exe. So when a user clicks on this link, config files are being loaded and written into, but there's no actual injection there or anything like that. Only if it can't write the config files, then the application crashes. So the server still has to be there, but there's no injection happening there. Instead, later on, the application does a separate call to PowerShell, which then, this happens. So yeah, be careful with UNC paths. Going forward, case number 3. This one was a bigger problem because this is all of Electron. So it's fairly common convention for command line utilities and everything that can be called from the command line to support this sort of dash syntax for separating or rather ending the processing of command line switches. So if you end your command with dash and a space, then anything you enter after that isn't considered a command line switch. And Electron supports that as well. And actually, one of the main workarounds mentioned by Electron developers as a workaround to CVE 2018-1,000,006, the official workaround was to include this double dash in your invocation of the app setAsDefault protocol client API. That way you wouldn't allow an attacker to pass any additional parameters. But because the original patch was based on comparing command line switches, a list of command line switches against the invocation of the app, it would also make sense to stop processing that blacklist once you found the double dash that's supposed to end your processing of command line switches. So that's what they actually did. The only problem was that, well, Electron sort of supports those dashes because Chromium supports those dashes. But Electron consists of Chromium and Node.js, and Node.js didn't support those dashes. So Node.js parsing continued after the delimiter, which meant that, well, bad things happened. This is from the screenshot of the blacklist earlier on, and you can see the blacklist starts with 2 very dangerous node switches. These 2 switches enable remote debugging. So a remote attacker would be able to remotely enable remote debugging. So yeah, that's way too many remotes. This was patched in Electron 3.0, and the patch was also backported to 2.something. The sad thing about that is that Electron doesn't mention the fix in the 3.0 release notes at all. It's actually tagged as no notes, the release. And the 2.0.9 release notes only mention this patch as something related to DNS rebinding, which doesn't really make sense at all. So it's not surprising that you'll still find these applications using pre-3.0 node Electron. So yeah, there's no public signal that would indicate that there's something wrong. And yeah, boy, was this easy to exploit. I went through the Electron application directory. They published this list of applications that are built on top of Electron. I went through that and looked at some of the more popular ones, some of the more big name ones. I ended up with RCEs in VK Messenger, in Postman, in the app I can't name yet, in Hyper, which is an Electron-based terminal emulator, and in Missive, which is an email app. And by no means did I comb through everything. So there's hundreds of apps in the application directory. I only looked at maybe 20 of them, and I found 5 apps that were vulnerable to this out of 20. So for one last time, let's go through the exploit flow. Here's the crafted URI. This one's for VK Messenger. There's the double quote, a space, 2 dashes, and then the inspect switch. We are binding to 0000 in order to make the debugger public. And once you click on this, the value of inspect gets passed to the Node.js debugger. So that starts listening on TCP port 5858, which comes from the command line, and just waiting for connections to arrive. The attacker, who has a remote machine, connects to the IP address of the victim and uses the Chrome DevTools protocol to launch an arbitrary command. It's just that simple. Now I have a couple of demos. Let's see if those work, because this is a live demo. I have them here. So this is a Linux server, or rather a representation of a Linux server running in a virtual machine. It's actually Kali Linux. And then I have another virtual machine, which is the Windows victim. Let's start off with the Mattermost exploit. I have here my SMB configuration. I'm setting, defining a share here in the Mattermost directory, making it public and making it writable. I also have here, if I look into the Mattermost directory, I have a bounce info JSON file, and I have a payload file. I can also look at the bounce info JSON file, so you can see it's referring to the payload file. And the payload is nothing complicated. It's just requiring the child process and executing calc.exe. So the way this works is I have a malicious web page here on the victim's machine. It has a link pointing to a Mattermost URI, which when I click on it, Edge will ask me if I want to open Mattermost. Sure, I'm just trying to visit some chat window or whatever. Let's open that. And it pops up the calculator. In the background, it's making a SMB call to the server and loading configuration files and then executing from there. The victim would never know that anything like this had happened. The other demo I have is for VK Messenger. This one works a bit differently. So the way this one works is I start with the link. I click on the link first and launch VK Messenger. And now it's already silently in the background listening for incoming connections from my malicious server. So let's make that happen. I have here a tool which I've written. I have node dev exec, which takes as its parameters a domain name, or rather a host name. Let's specify that, and then a port and a payload. And when I call that, suddenly here something's not working as expected. Demo effect. Let's try that again. Demo effect. Oh yes, the host name was wrong. Yeah, 5858 and cat.exe. Now that should work. Suddenly we have the calculator popping up here. So that's as simple as that. Now let's go back to the slides, if we can somehow. Yes. Okay, so you saw there was a command line tool I was using. That's actually just a simple wrapper for Chrome remote interface, which is a publicly available client for the DevTools protocol. You could obviously do the same thing using the DevTools integrated with the Chrome browser, but using the command line is a bit quicker, especially when you're testing multiple apps in a row. The tool is available on GitHub already, so if you memorize the URL at the bottom of the screen, you can actually go there and download it now. But if you don't want to start memorizing that, you can just memorize my username instead, and I'll make the gist public after this talk. It's private at the moment, but I'll make it public afterwards. Anyway, my work obviously didn't end when I managed to hack all the apps. That's not how it works. Someone had to fix those bugs, and that meant coordinating disclosure and talking with the vendors, and I tried to find the easy way out, and that just ended up with me doing twice the amount of work. Here's a few lessons from that. So I haven't been in contact with Electron, but they've done quite a bit. Sorry. Okay, let's go through this one first. So as I mentioned, all of this started in February 2019. I was casually poking at one of the apps when suddenly all hell broke loose and I had 7 RCEs on my hands. Disclosing all of those privately one by one would have been a huge effort, especially when many vendors still today don't publish proper security contacts and don't, even behave politely towards researchers. I wanted to come up with some better strategy, so the obvious solution was Trend Micro's zero-day initiative. They buy, research, and report vulnerabilities responsibly to vendors. So that would allow me to have a single point of contact and let them take care of contacting the vendors. So that's what I did. I contacted ZDI and reported these to ZDI. I submitted my reports near the end of February, and just a couple of days later I got a response already. It just wasn't quite what I'd hoped for, so without even looking at the exploits or the vulnerabilities, ZDI had already determined that they weren't interested in 5 out of the 6 apps. They just didn't want anything to do with those. So they wouldn't buy those. Anyway, the initial response was super quick, but one app was still remaining that they didn't comment on. They didn't say anything about VK Messenger. So apparently they were interested in that one. Unfortunately, the process from there onwards was not as quick as the start had been. So it was basically complete radio silence from ZDI for the next 3 whole months. What was more disappointing was the response I finally got. So in June, ZDI emailed me and told me that they had tested the VK Messenger exploit and they had come to the conclusion that this doesn't work. It's not a valid exploit. It's not working. And what had happened is that 3 months had gone by and VK Messenger had already upgraded the version of Electron they were using. It was no longer exploitable. ZDI was testing the latest version and that didn't have the vulnerability anymore. So since ZDI wasn't interested in any of my exploits, I had to report them individually to all the vendors anyway. And I had to retest everything because it had been so long since I originally found them that others might have fixed theirs as well. Luckily, VK wasn't the only one who had implemented fixes, so I didn't have to contact all 6 different vendors. I just had to contact a couple of them. And it ended up with me working on one of those apps full-time as a security professional, product security engineer. So all's well that ends well. So since 2018, since CVE 2018 1,000,006, Electron has done a whole bunch of things. The original blacklist they implemented is, well, it's been updated, and it's been updated again, and now it's no longer 1,300 items, it's 0 items now. They're no longer using the blacklisting approach at all. They've also twice changed the way they handle command line switches. The good thing is that I'm not currently aware of any way to exploit the original CVE 2018 1,000,006 vulnerability. So I think they have it in sort of a good order at the moment. The bad thing is that they still haven't published any advisories about this after CVE 2018 1,000,006. And URI handlers are still being registered in the same way, so they haven't addressed the root cause of the issue. They've just changed the way they're sort of mitigating the issue on top of that. But anyway, developers still don't know that there was something wrong in the original patch. Microsoft has also done some things. So the major thing that you might notice is that if you try one of my exploits here on an up-to-date Windows 10 machine, you can no longer open any of the malicious links from Internet Explorer or Microsoft Edge, because those no longer allow special characters in URLs. Instead, they automatically, silently percentage encode the special characters, so that, for example, space becomes %20. You can still open those types of links from other apps, though, so the Windows patch isn't foolproof. For the developers and security people who are probably here in the audience, there's a couple of interesting takeaways from this. So first of all, the app.setAsDefault protocol client is a very dangerous API, and scheme handlers in general are a very dangerous attack surface. It's difficult to even spot all the things that can go wrong with them. And if you find yourself using one of those, or looking at the code base that does use one of those, you should probably think twice that is this something that really has to be here? Is it actually necessary? And if it's necessary, is it being used correctly? Secondly, platform features like Windows support of UNC can have really unexpected side effects if you're not accounting for them. Even if you're working on a cross-platform application on a platform-independent framework, you should also aim to know the platform you're actually shipping those applications on. Otherwise, you might then end up shooting yourself in the foot. And finally, Electron has this bad habit of not publishing security issues and sufficiently informing the developers about them. So it's critical to keep your frameworks up to date, even if there's no publicly documented vulnerability in that framework. Since May, Electron has also adopted this 12-week release cycle where they release a new major version of Electron every 12 weeks in order to keep up with 6-week cycle of Chromium. And so that means that because they only support the last 3 major releases, if you're deploying an application now, you're going to have to upgrade the framework in around 8 months, or you end up with an unsupported version. That's all I had. Thanks for your time. And
amazing. Thank you, Juho, for the presentation.